Welcome back, class. In this video, I want to talk about something called buffer solutions. So what is a buffering solution? Well, it is a solution that resists changes in pH, and it accomplishes this by neutralizing added acid or base, if you want to refer to them as impurities, right? And so there's two types of buffers. We can have an acidic buffer, if you will, which is based on having both significant amounts of a weak acid and its conjugate base in solution. Or we could have a basic buffer, which contains significant amounts of some weak base and its conjugate acid. Now, as we go throughout this section, this chapter, we're going to focus on a buffering system that has a weak acid and its conjugate base. But understand that we could also work with a basic buffer. Now, one buffer that's present in human blood, right, is this carbonic acid carbonate buffering system. Dissolved within the blood, we have significant amounts, or enough of carbonic acid and the bicarbonate ion, right? And so we can get a buffering system within the blood that allows the blood to compensate for changes in hydronium ion, right? So if you were to get impurities into the blood that were basic or acidic, right, they can compensate for those, allowing the blood to stay within a reasonable pH range when you have these kinds of impurities. So again, when we make this up, we literally would take a solution of a weak acid, like an acetic acid solution, and we would mix it with a solution of its conjugate base in the form of course, an ionic compound, because that conjugate base is going to be an anion. So we might mix it with a solution of, say, sodium acetate. And the end result is we create a solution that contains significant amounts of both the weak acid, acetic acid, and its conjugate base, acetate ion. Okay. Now, this buffering system is going to be acidic, right? It's going to operate in an acidic base because that weak acid, that acetic acid, is going to produce hydronium ion. Now, somebody might want to raise their hand and say, oh, well, you have a solution of sodium acetate, right? And the conjugate base of a weak acid is a base. And that base can undergo an ionization to create hydroxide ions. That is true. But what we have to remember is that the conjugate base of a weak acid is going to be a weak base, but it's going to be a weaker base. So in other words, if we were to look at the K values, the equilibrium values, that weak acid is going to have a larger Ka than the conjugate base is Kb. And so we're going to end up generating more hydronium from the weak acid than hydroxide from the weak base. And so that buffering system is still going to be acidic. As we'll see, not as acidic as the actual, if we just had a solution of the weak acid. So how does it operate, right? How does it accomplish this goal of maintaining a similar pH? Well, if a strong base is added, right, the acid component of our buffer jumps into action and neutralizes that strong base, or the hydroxide that's coming from that strong base, as it's added, right? And it converts that into water and the conjugate base of the weak acid. So, one way to look at the net effect here is the HA concentration goes down a bit, and the A- concentration of our buffering system goes up a bit. So if we imagine that we start with equal amounts of these two parts of our buffer, then if we add a strong base, right, we're going to lose some of the HA, the acid component is going to drop down, and the conjugate base component is going to go up. Now, that shift in equilibrium is going to be somewhat compensated by the effect of Le Chatelier's principle, right, on our acid equilibrium, right? So if we just, again, remind ourselves that we have an equilibrium here of our weak acid producing hydronium ion and A minus. So as this A minus creeps up and this HA creeps down, right, this equilibrium is going to be disturbed. And so it is going to try to compensate, in this case, by shifting the equilibrium back toward HA to try to regenerate some of that HA and get rid of some of that extra A minus that's been produced. Now, of course, as we saw, it's not going to get it back to the exact same concentrations as before, right? Because you've added other things. We're going to get back to equilibrium, but not the exact same equilibrium, or not the exact same concentrations that we were at before. So it's always important to realize that these buffers don't prevent pH change. They just minimize the pH change, right? They keep it within a more narrow range than you would see, for example, if I added this strong base to just a water solution, right? Now, all of this is predicated on the fact that as long as the amount of sodium hydroxide or strong base doesn't exceed the amount of the acid part of our buffer, right? Eventually, if this runs out, then of course it's no longer a buffer solution anymore because we don't have both parts, and so then we're going to see rapid pH change. So we can go through exactly the same analysis, but in the opposite way if we add an acid. So if we add a strong acid, what we would see is that the basic part of our buffer jumps into action, the conjugate base. And so we're going to lose a little of our A minus, and we're going to create a little of our HA. But in the same way that we talked about last time, that acid ionization equilibrium is going to shift. In this case, it's going to shift, in this instance, it's going to shift toward the product side to get rid of the extra HA that's produced and regenerate some of the A minus. Again, so while these concentrations will change, right, they won't change as much because the equilibrium will adjust to sort of somewhat compensate for this, reducing the effect, if you will. And so we have this system where we have these two parts of our buffer. One can respond to added base impurity, one can respond to added acid impurity, and therefore keeping the pH within a range. Now, as I was sort of mentioning, right, and so these slides are a little bit repetitive, that Le Chatelier's principle is coming into play here, right? So if we go back to addition of a base, we have, Le Chatelier's working on that weak acid equilibrium that I talked about, right? And so as we create more A minus, right, or create more HA, right, we're going to, compensate here. So in this particular case, right, since we are adding an acid, the base is going to jump into play, and we're going to the acid part is going to come into play, and if we were to add acid, the basic part of our buffer is going to come into play. So if we think about this Le Chatelier's principle, and we understand that buffers contain significant amounts of the weak acid, these weak acid molecules react with any added base to produce, again, the conjugate acid or the conjugate base of our weak acid and water, right? And so, again, we see the A- go up, the HA go down, and this original equilibrium that we talked about can compensate for that. By shifting the equilibrium. Again, same idea. If we add the acid, we have significant amounts of the conjugate base, the A minus. So when acid is added, it's going to react with that A minus again to produce the HA. So the HA is going to go up. And as the HA goes up, that original equilibrium is going to shift to try to get rid of it, or it's going to shift toward the product, right? And allow the concentrations of HA and A minus to stay the same. Right? So the bottom line with all of this, right, is understanding that as you add the impurities, by having both of these things present, we can maintain fairly constant concentrations of hydronium ion and our two components, right? They're going to minimize the shifts in these concentrations. Now, we get even more benefit, right, if we set up our buffer as we usually do as a common ion. Right? So when we mix this, we combine a weak acid, and we don't just use some base, right? We use specifically the conjugate base of that acid because it would contain what's called a common ion. Having this common ion lowers the ionization of our weak acid, right? Because, right, if we just have the weak acid in water, right, it's going to have some sort of percent ionization, whatever that is. But by having already a large initial amount of that A minus, right, it's going to reduce the tendency of the equilibrium to make more A minus, and so it's going to lower the percent ionization of acid because you have that common ion effect. Now, because of this, right, we see the pH of these buffer solutions be acidic, but not as acidic as if we just had the weak acid there. Now, this is probably not just generally not a surprise, because we might imagine that if we were adding in a base, right, even a weak base, right, we might keep the solution from becoming quite as acidic, right? And that is true, but this is kind of the way we can explain it using Le Chatelier's principle. So we can show visual evidence that this is indeed what happens, right? A pure or a 0.1 molar acetic acid solution has a pH of around 2.9. If we take that solution and combine it with a 0.1 molar of the common conjugate base, the acetate ion, we still end up with an acidic solution, but not as acidic, right? So we end up with a more weakly acidic solution. Now, just as a comparison, the acetate solution, right, has a very basic pH, right? As you would expect, it is a weak base. But again, because the acid, right, is a stronger weak acid than the base is a weak base, we end up overall with an acidic buffering system when the two concentrations are equal.